Welcome back to CS 520. In this session I want to talk about concurrent hash tables. These are hash tables that can be accessed simultaneously by a group of threads. Let's back up and remember what I mean by a hash table. Hash table is a data structure for storing symbol data pairs. So the assembler is a typical use of a hash table where we're storing labels as the symbols and addresses as the data. My view of a symbol table my view of a hash table consists of a control structure that contains things like the length of the hash table, in other words, the number of buckets in the hash table, and a pointer to the array that stores the bucket pointers, where each bucket itself is a linked list. And the nodes on this list contain a pointer to the symbol and a pointer to the data. So each node here carries one symbol data pair. And obviously the third component just is the link to the next item in the bucket. And our primitives for manipulating symbol tables is this list, create a table, delete a table, look up a symbol and get the data associated with it, or update the existing data, or install a new piece of data for the symbol, and then routines to allow us to iterate through the contents of the table. When we start thinking about having multiple threads access the table, and what I mean by that is we're just going to focus on allowing lookup and update to be performed simultaneously by a set of threads. We'll assume that the create and the delete and the iteration will be done in a single threaded mode. But when we start thinking about doing concurrent lookups and concurrent updates, there's two basic issues. One is safety, right? We don't want two updates to collide. If we're installing a new node onto a linked list, we want to make sure as we break the links and so on that we don't interfere with another thread either reading the list or also simultaneously trying to install in that linked list. So we don't want to have multi-threaded access actually break the data structure. So that's the safety issue. And then there's a scalability issue. How many threads can we support accessing the table at once effectively? We'll try to look at both of those as we go through this. Let's start with safety, however. Again, key safety issues, for instance, two threads inserting at the same time. It could be the same bucket, in which case we have to worry about them breaking links and at the same time and perhaps destroying that linked list, or even having a race condition on updating the data for a symbol that's already in the table. So the obvious solution to the safety issue is just lock the whole table. In that case, we might extend the control struct to include a mutex. And upon entry to lookup or upon entry to update, we simply lock that mutex, do our lookup or do our update, and then before we return, we do an unlock. Thinking about that, though, leads us to the issue of scalability. If you think about it, a single lock on the whole table will serialize the access to the table. All the threads will have to take turns accessing the table. And all the threads are contending for a single lock. So that's going to limit the scalability. What if we use multiple locks? Well, this would be called lock striping. So we'll assign groups of buckets to locks. And we'll put multiple mutexes in the control struct, one for each group of buckets. And then we'll map buckets to mutexes by taking the bucket index modulo the number of mutexes. So now two threads can access a symbol table at the same time if they are not accessing buckets in the same group. So this would allow concurrent access to the table. Okay. An alternative version of that is, instead of using mutexes, we might use something that I call thin locks. If the level of contention is expected to be low, then we can use a lightweight locking mechanism. So if most of the time when you go to lock a group of buckets, you expect to not find it already locked, then we might use the compare and exchange instruction and do busy waiting and make a number of tries in case the compare exchange doesn't succeed right away, and then call yield, which means that the running thread would give up running, let another thread run. We'll call yield if we can't attain a lock after some number of tries. I'm not going to go into more of this because we're going to have a separate lecture next week that will discuss this with respect to doing it on actual Intel hardware. So we'll come back and look at that again later. Another way we might address the scalability issue is why not allow concurrent reading? Why not allow multiple threads to read the table at the same time, even if they are accessing the same bucket? Right? Read access can't have anything go wrong. You know, we're not breaking any links, we're not overwriting any data fields. So the basic idea here is if readers are reading, then block any writers that show up that want to use the table. And if writers are writing, then block both readers and writers. So at any point in time, we could have a group of readers reading, but we can only have one writer and nobody else doing anything if there is a writer writing. The question is, how would we implement that? This is an instance of a problem called the readers and writers problem. We want to allow multiple readers but only one writer. So let's look at a solution, again using pseudocode for the thread operations. You know, the data that I would have would be a mutex and a couple condition variables, one that the readers would wait on, one that the writers would wait on, and then 4 counts. A count of the waiting readers, a count of the waiting writers, a count of the active readers, and a count of the active writers. And these counts would be initialized to 0. So let's look at what a reader would do in order to get the permission to read. First of all, we'd lock the mutex, which is what's protecting access to this shared data. And a reader can't read if there's any writers writing. So once it locks the mutex, it would check the writers count. If it's greater than 0, it would mark itself as being a waiting reader. In other words, it would bump up the count of waiting readers, and it would wait on the readers condition variable. When it's signaled, then it would decrement the waiting readers count and check again to make sure there's no writers. Again, remember the wait, there's a delay between the signal is received and when the mutex is reacquired. So the state of this data could change in that interim time period, which means we got to come back with a while loop and check our condition, right? In order for us to proceed, we need the number of writers to be greater. We need the number of writers to be equal to 0. So we continue waiting if the writers was greater than 0. At some point, though, hopefully we would escape this while loop and we would become a reader. We would bump up the readers count and we would unlock the mutex and then go about our business doing the read of the table. Okay, in my formulation here of hash tables, the read operation is the lookup routine, and the write operation is the update routine. Let's look at what a reader does when it's done reading. Okay. Again, it's going to lock the mutex that protects the shared data that's tracking the state of the system. I want to no longer be reading, so I'm going to decrement the reader's count. And I'm going to check to see if there's anybody waiting that I can wake up. So I check to see if there's any waiting writers. And also, I have to be the last reader in order to wake up a waiting writer. So I'm going to check and make sure that that when I decremented the reader's count, I drove it down to 0. I'm the last reader. If that's the case, then I can signal a writer. Notice it's a signal, not a signal all, because I only can release one writer at a time. And then I do the unlock. Again, I'm assuming, I probably should have said this first, but I'm assuming that the reader would go through these steps, right? It would invoke this reader start code that we just looked at. It would then perform its read access to the table, and then it would invoke the reader end step. Okay. Well, what about the other half? What about the other half? We need code for the writer to start and the writer to end. And what I want you to do is I want you to try to write that code yourself. And one important note is, you could have both readers and writers waiting when a writer completes, right? Because when a writer is writing, other writers can't write, and other threads that are reading can't read, so they'll both be queuing up in the two condition variables. And you'll actually have to make sort of a decision about what are you going to do when the writer finishes and it looks and there's both readers and writers. Are you going to release another writer, or are you going to release all the readers? I'm not sure there's a right or wrong answer there. It's just that you have to make a policy decision. Okay, but try to figure out how to write the code again in terms of those pseudocode for lock and signal and wait, and perhaps you want to use signal all as well. Okay, one last thing here. This is not everything there is to learn about concurrent hash tables. There's also possibilities of doing lock-free, wait-free hash tables. But these are more advanced approaches that are beyond the scope of what we want to talk about in this course. If you want to learn more about this kind of thing, I recommend taking CS 735. Okay, I'm going to stop there. I just wanted to give you a brief introduction to the issues of when you're sitting down to implement a concurrent hash table, a hash table that's going to support multi-threaded access to the table.